So I'd like to address a question that sometimes comes up, which is electrical resistance good or is it bad? And the answer is that it kind of depends. A resistor is a specific type of circuit component that turns electrical energy into thermal energy. And as it says here, that could be because you want it to be a heater. For example, on the left here you have that resistor, that orange glow, being used as a heating element in an oven. Or on the right side, you could have resistors that look like these. That's what those cylinders with the paint stripes on them are. They are resistors in an electronics circuit that are used to protect other components in the circuit and control how much current is going through any particular component at any given time. Resistance can be bad, though. It is an inherently inefficient part of any conducting material. So things like wires or even in your voltage sources, there's a resistance in there that is dissipating energy that is simply an inefficiency. So it's sometimes good and sometimes bad is the answer that we have. When we talk about electric power, the equation that we're going to want to talk about is that the power in a circuit is equal to the current times the voltage. It's still true that power is the rate at which work is done, or the rate at which energy is transferred or transformed. So delta E over delta T, or work over delta T. I say that's still true because it's something that you should have seen in Physics 140, but depending on the 140 section that you had, for example, if you were in my section, we didn't talk about this. We very briefly mentioned that this is true, that there's the rate at which energy changes is called power, and we didn't spend time on it. Here we will spend time on it, and I want to emphasize that this power is delta E over delta T, the change in energy over the change of time, but we won't think of it that way in most of our problems. We will think of it as current times voltage, and we could prove that that means the exact same thing. I also want to point out the third and fourth parts of this equation here, the I squared times R, or V squared over R. Those are equal to power if you take IV and combine with it Ohm's law. So for example, if you know the resistance of a circuit and the voltage, but not the current, or you know the resistance and the current, but not the voltage, you can use Ohm's law to find the missing piece and then find power. Or you can just say that you know that these are the combination, I squared R and V squared over R are the combination of P equals IV and Ohm's law. Either way, whether you're talking about work over time, change of energy over time, or one of these equations on the screen right now, the unit of power is the watt, and 1 watt is equal to 1 joule per 1 second. The way we would use that equation in a electrical example problem like this one, if a flashlight has a 4.8 watt LED light bulb and the circuit runs on a pair of 1.5 AAA dry cells that are put together in such a way that they make a 3-volt battery, what is the current in the bulb? Well, the current is related to the power and the voltage through the equation that we just saw. I know that the 4.8 watts is the power because that's what watts are a unit of. So I would rearrange this to say that the current is equal to the power divided by the volts. The power they gave me is 4.8 watts. The volts they gave me is 3 volts. So the current would be 1.6 amperes. That seems pretty straightforward, and it is. And we'll do some problems that are more complicated, of course, to make sure that you know how to make that more complicated. More than just putting numbers into equations, though, I really want to talk about how a light bulb even functions and how other circuit components will function. We're going to start with this old-fashioned style light bulb right here, which is called an incandescent bulb. The word incandescent literally means that this gets hot enough to glow. How that happens is that the glowing part there is a resistor. So that glowing part is turning electrical energy into thermal energy. And if it turns it into thermal energy enough, then it glows. That's why an incandescent light bulb is filled with either an inert gas or a vacuum, is that you don't want the high energy transfer that's happening in that filament to also get involved with some sort of chemical reaction with the gases in the atmosphere. For any circuit component, you have to have a wire that goes in on one side and out on another, or else the circuit component is not part of a circuit. The whole point of the word circuit is that you have to be able to trace it in a complete cycle from the voltage source through the materials and back through the voltage source. We're definitely going to want to play around with the PHYS simulations for circuits to get a better sense of how that works. But there are some items, for example, like a light bulb, that most people don't think of as having two connecting pieces because you just screw the light bulb in and it works. And I want to point out that even in situations like that, there are two connecting pieces. This metal part right here that has the actual screw ridges is how the electricity could get in or out. And then down here at the bottom is another metal piece that electricity could get in or out. And this little black piece is an insulator. And you usually would not need to know any of that because you just put the light bulb into the fixture, flip the switch, and it works. But here we're trying to talk about exactly how it works. How it works is that the charges can move in through here, up through the middle of the bulb, through this filament where the electrical energy is turned into thermal energy, hopefully making it hot enough to glow, because that's the useful part of a light bulb. And then the charges come down this other wire and out through the rest of the circuit by this metal screw piece. That is the second part of the connecting this bulb to the circuit. I want to emphasize that this is true for DC circuits and AC circuits. If you have ever plugged something in, then surely you know that there are two prongs on a functioning plug. And most items that you plug in, you can even take a look and see that there's two different wires leading from the plug to the item. That's not true for everything, of course. There are two wires in there, but you don't always see them both. Sometimes they're wrapped in what looks like a single cable. And that's sort of what I'm getting at, is that our familiarity with this can be really confusing if we stop and take a look and say, wait a minute, why are there two prongs but only one wire? And that's on the inside of the wire, there's actually two. And in this case, it's more obvious that there's two. Again, we will get to play around with these with the PHYS simulators in class, and hopefully that will answer a lot of questions about how circuits can be made to function.